So if you missed yesterday's lecture, the slides are posted. What we went through and covered was chapter 15 and 16, 14 and 15, 15 and 16, 15 and 16. So we did the acid bases, buffers, that kind of stuff. We did a lot of stuff with buffers. Okay? So the question that first came up here was from, I think it's the practice final, right? What number is it? It's a Roman. Roman numeral 8, it's a chapter 19 question. It should be summer 12. And what it asked for was the time necessary for a particular result. So we want to solve for the time. If we're given a current 10 amps, and we produce 1.42 moles of bromine. Okay? So we want to be able to figure out that time as far as all these relationships go. So based on the numbers given, we don't see a time unit right away. Is there something you can do to convert either moles or amps to get a time unit? Amps can be converted to generate a time unit. Amps are the equivalent of a coulomb per second. So we can introduce a time unit. Okay? If we wanted to start with the 10 amps, we could go through and do that. If we converted, say, 10 amps, 1 amp is 1 coulomb per second, what would our units come out to? So if we did this conversion, what would we get? That equals
1 coulomb, 10 coulombs.
10 coulombs per second. Does that put our time in the correct numerator-denominator spot? No. Which means if we're going to start, we're going to need to realize that we're going to have to divide by the amps so that our units flip-flop on this. Okay, so what I would start with, just go ahead and say, okay, 10 amps. So 1 over 10 amps. There's no unit on top because all we're doing is dividing by that number. Okay, so we don't have to have a unit on top to do this. Do our conversion factor, 1 amp is 1 coulomb per second. Our net result is going to be, if we look at the units, which I'm going to erase here real quickly, it'll be seconds over coulombs. It's a good deal. We've got our time unit where we want it to be. We want it to be in the numerator because that's how we report time. Okay? But our problem now is that we've got coulombs, so we have to somehow get rid of the coulombs. Can we, whoops. Okay? Can we get rid of the coulombs with any conversion factor? Can we convert coulombs to anything else? What can we convert them to? What's that? We can use Faraday's constant, which says 96,485 coulombs are equivalent to 1 mole of electrons. So if we follow our unit trail so far, we're now into per moles of electrons, or seconds per mole of electrons. Okay, so we're moving closer, but we still have that mole of electron unit showing up. Can we get rid of the moles of electrons? Do we have something that we can convert the moles of electrons to? We would need a mole-to-mole ratio, which is found in a balanced equation. So far, have we addressed a balanced equation? No. So what we're going to have to do is go back and say, okay, how did we do this reaction? So we looked at the formation of bromine gas. What was that made from? Magnesium bromide. What's the charge on bromide? Or what's the symbol for bromide? Let's try that. Br minus. Okay. We need to go through and balance our half reaction. Is it balanced? No. What's the thing that you see is not balanced? So the very first thing that you would need to evaluate is what? The number of elements, not your charge. Okay, so if we go through and look at that, our elements aren't balanced, so we need to fix that. What do we need to do? put a 2 in front of our bromide. Now that our elements are balanced, now we can balance charge. Is our charge balanced? No, what do we have to do? We need to put 2 electrons on the product side. Okay? So what does that now give us? We know that 2 moles of electrons is related to 1 mole of bromine. So we now have seconds per mole of bromine. Okay, that's helpful. But we still have that mole of bromine unit. Can I get rid of the moles of bromine unit? I know I made 1.42 moles of bromine. What are my units now? Seconds. Make sure you check the question to make sure you've answered what the question actually asked. If the question asked for units of minutes, your answer is wrong. Okay? I think the question asked for seconds, something I typically do because I assume you can do minute to second conversions. In fact, I assumed you could do that before this class started, so there's no point in me testing you on that. Okay? Questions about that? So a lot of this is just trying to set it up and get your units where you want them to be. That's what all dimensional analysis problems are. If you're trying to solve for a pressure, you need to get a measurement or a unit of pressure in your numerator because that's how we monitor pressure. Okay, ATMs in the numerator. Do whatever you've got to do with the individual terms you're given to get that unit in that appropriate spot. What if you had multiplied by amps instead of divided? If you go through your whole calculation and you assume you did your unit swaps appropriately, so that means all of our conversion factors flop, you'd have to trace your units carefully, and the unit you would end up with at the end of this would be per second. Okay? Is that a time? No. So what would you have to do? Flip that number and now you have the correct answer. Okay? So you can go through and solve the problem in any particular direction. You just have to make sure that when you go through and do that, your units check out and you use those units at the end to decide what your answer is. Make sure you've appropriately canceled your units. This is why when you go through 151, in theory, your professor insisted that you tracked units in every single position. This is why in lab, when you write out moles, I typically have given you a hard time because I don't know what that's moles of. Okay? If that's moles of copper, that's something entirely different than moles of electrons. That extra little piece of information in your unit makes a huge difference in trying to solve your answer. Okay? The one big place that students will typically mess this one up, okay, beyond the dimensional analysis issue, is that when you go to balance the problem, the first response is, oh, it's bromide to bromine, charges don't balance, we add an electron, oh, now it's a 1-to-1 ratio. When can you balance charge? Only after you balance all the atoms. Okay? Balancing charge is the very last step. Okay, so when you go through to come up with your balanced reactions, make sure you balance everything except for the charge, except for those electrons, then you can bring the electrons in. Okay? Questions about that? So, in kinetics, what we're looking at is a study of rates. Hey, that's fun, we just looked at time. Okay? So when we go through and look at these, there's a couple different ways that we can come up with rates. The standard way that we could go through it is the way we've seen it everywhere else. We're looking at some change of some unit, it doesn't matter what unit, per time. So our rate is always a per time calculation. One of the things that we address, let's see, is it up there? Is how we refer to these things. A rate of change implies a neutral observer. So we don't really get to see a directionality according to our numbers. So when we go through and calculate a rate of change, the sign will naturally tell us what's happening with the reaction. If we look at an observed change, or sorry, an appearance, a rate of appearance, That assumes we are looking in a direction where it should be appearing. So if we calculate a rate of appearance and we see a negative value, what does that mean? It's doing the opposite of appearing, which is disappearing. So those negative signs, or that positive negative, is just implying a directionality to what's happening with the reaction. Make sense? Kind of? So we went through and addressed lots of different questions along those lines. Which way is a cursor moving? That kind of fun stuff. We could then apply this back to an individual reaction. And if we wanted to look at the rate of change of something, let's say we go through and we calculate that the rate of change for A. To calculate that, we would look at the change in the concentration of A per some unit of time. If we looked at our units on this, this would be moles of A per liter times seconds, correct? What if I wanted to convert the moles of A into the moles of anything else, say the moles of B? What would I need to do? I need to multiply by the mole-to-mole ratio. What's the mole-to-mole ratio? So moles of A needs to be on the bottom, moles of B needs to be on the top. What's our ratio? Comes from the coefficients in our balanced equation. In this case, for every B moles of B, we have A moles of A. And we can go through and come up with similar conversions all the way through this. And what someone went through and did is started to compare and say, oh, this is very similar to if we now just kind of group like terms. Whoops, didn't want to see that. And that's the equation that we get at the bottom. You'll notice one big difference. In that conversion, we don't, or in the initial conversion we looked at, we didn't look at a sign. Why did we not look at a sign? When we converted A to B, what's the relationship between A and B? Are they doing the same thing or different things? The exact same thing. And then we know that because they're on the same side of the reaction. As soon as we try to convert to something across the reaction, it's now doing the opposite of what we were initially doing. If we do the opposite, what does that mean happens to the sign? The sign must also change. As a standard notation, if we look at a reaction, typically when we set these up, what happens to the concentrations of our reactants? They disappear, okay, or they decrease. So if we're going to relate our rate of change of our reactants to our products, we're going to also have to introduce that sign, okay, so that we can compare across that equation. That's where this relationship comes from. Okay? Questions about that? Rate laws. So when you're given an individual reaction, you should be able to come up with a generic rate law. So we take a look at that top rate expression. So first off, when we're looking at rate laws or rate law expressions, it's always going to start with rate. Rate equals something. We're looking at a rate law, so it makes sense to be looking at the rate expression. So our rate is going to be equal to some constant. Unfortunately, we picked a stupid symbol for our constant because it's easily confused, but it's a lowercase k times the concentrations of our reactants. Why do we typically not include our products? Most reactions, the products don't do anything. In most cases, we do not get a product feedback loop slowing the reaction or speeding the reaction for the most part. Where is there a big exception to that? Biochemistry. Nearly everything done within your body or in any living organism has feedback loops where a product shuts down the reaction or speeds the reaction. So when you move into biochemistry, you end up drastically changing the kinetics of reactions, and you end up having to evaluate all sorts of different things and different variables because your products feed back into the reaction. It makes the problem much more difficult. which is why we don't look at it now. We wait for biochemistry to do that, thankfully. Okay. Next part of the rate expression is the powers to which we hold those concentrations of our reactants. Those powers must be experimentally determined. So there's two ways we can determine those experimentally. One, we look at actual data. So we go through and we look at the concentrations of our reactants and, in theory, our products, because there is the potential for products feeding back in. And we'd look at the rate for that reaction. And we'd try and set up an expression where we could see how the rate changes in comparison to how the concentration changes. If we had multiple reactants, as we did in this case, what two experiments would we compare? We want to pick two experiments where one of our reactant concentrations does not change. Why? That simplifies our problem. So that when we go through to try and determine how our rate changes with respect to the concentrations, if one of our concentrations never changes, it's of course not going to affect the rate because the concentration didn't change. That simplifies our rate expression and allows us to solve for the order of the one that did change. All right, so that's where we compared and matched things up to try and determine what different things occurred. Based on that, you could then determine the order for that reagent. You could then go through and pick another pair of experiments and try and determine the order for the other reagent. Vaguely makes sense? The other way we can determine these experimentally is, it's up there. We would go through and look at a mechanism, okay? Or we could look or be told that it's an elementary step. If it is an elementary step, what we're saying is that those exact numbers of molecules all come together at the exact same instant and we generate our product. That means the coefficients are the orders. So it simplifies our mathematics a lot more. So you can either be told that it's an elementary step or you can be given individual mechanistic steps. When we come up with a mechanism, the intent of that is to try and define how the reaction worked. So we're going to go through and simplify it as much as possible, and we're going to take individual molecules and have those molecules react with each other, or have one molecule react with itself, or decompose. So what we end up evaluating is simple reactions. We can then go through and look at which one's fast, which one's slow, and try and manipulate our equations. I think I've got one like that up on the next slide. Okay? Questions about that? Let's see, did I put one up there? I did not. Should I try and come up with a quick example on that? Or slow versus fast? Okay. Anybody have an exam handy that has one? That doesn't have one.
13.
Oh, geez, a ridiculously long one. Okay. So this is an old exam, right?
Yeah.
Do you know which one it is?
12.
Summer 12. Which exam? Is it the final?
Version A.
But the final?
Yeah.
Summer 12 final, Roman numeral 1. We're looking at rate expression. Given the following mechanism. So we are told Cl2 Cl plus CHCl3 K2 and I'm going to change the question from what's actually on here. We'll look at a couple different examples. In fact, we'll look at 3 different examples. Thank you. If we want to figure out the overall rate law, one thing that can be helpful is to figure out what the overall reaction is. How do we figure out the overall reaction? We're going to add them all up. Go over and we go through and do that. We'd get Cl2, CHCl3 goes to HCl plus CCl4. If we tried to come up with a rate expression for that, what would our rate expression look like? Rate equals K, concentration of Cl2 to what power? X. We do not know that order. Okay, this is an overall reaction at this point. Okay, in fact, by definition, it is not an elementary step. Times the concentration of CHCl3 to, again, some unknown order. That is a valid rate expression, okay, but as with most things, if it's not useful, it's pretty pointless to look at. Do we know the orders? No. Can we use this rate expression? No. So it's a reasonable first step, but we're kind of dead in the water at this point. We don't know those orders. We have to come up with some way to figure out those orders. To do that, we go back and look at experiment. We could look at concentration changes and see how that affects the rate. We're not given that information. We're given a mechanism. So what do we have to do? We go back to the mechanism. We have to think, okay, what step is going to matter the most? It's always the slow step, every single time. So let's say the first step is the slow step. So this is problem number 1. Okay? If our first step is the slow step, everything that happens afterwards happens so fast that I don't care about it. The only thing that's going to determine the rate is what's happening in that very first step. Okay? So what is the rate of that very first step? Or a rate expression? It'll be K1, because we're looking at the forward direction. I know my arrows kind of suck on that. Times the concentration of Cl2. My overall rate is dependent on that. Every rate thereafter is irrelevant, which means what is my overall rate expression for this reaction? Rate equals K1 times the concentration of Cl2. That's what we'll look at next. Okay? Before we say that's okay, we also need to make sure that we can figure out everything within this. Make sure it's useful. Okay, first off, do we know the order? Yes, we do. Why do we know the order? The first step is, by definition, an elementary step, which means the coefficients are the order. Okay, that's one of our benefits behind a mechanism. So we do know the order. Is the concentration of chlorine something that I would know? Go back to the overall equation. Does it show up in my overall equation? Okay, yes, it shows up as a reactant. Is it reasonable to assume that we would know the concentrations of the reactants that we put into the reaction? Yeah. Okay. Rate we can monitor by running the individual reactions, so that's something we don't need to worry about. If we know the concentration and the order and the rate, what can we do with the rate constant? We can solve for it. So we know or can find out with a simple experiment everything within that. Okay, so that is a valid rate expression. It is useful for us to go through and use that. Okay? What happens if instead of that being the slow step? So now it's when it gets tricky. Okay, as the problem actually suggested. Let's say the second step is our slow step. Every step that happens before and every step that happens after happens so fast that it does not affect the overall rate. Which means the overall rate for my reaction is going to be equal to the rate for step 2. What is my rate for step 2? rate equals my rate constant for step 2 times concentration of Cl to what power? First. Why is it to the first power? Because the coefficient is 1 in that equation. Why can we use that? Because it's an elementary step. Every mechanistic step is an elementary step. We're allowed to shuffle that coefficient across. Times the concentration of what? Okay. That is now an overall rate expression, just like we had at the bottom there. So now what we've got to do is evaluate. Is that expression useful for us? Will we be able to figure out the rate? If we do the experiment, we can monitor the rate. Okay, that's a reasonable assumption. Okay, how about the concentration of CHCl3? Is that one of the species in my overall reaction? Yeah. Shows up as a reactant. If I'm putting it together, I'd better know what I'm putting in there. Okay, that can be really, really dangerous if you don't. How about concentration of Cl? It's not there. How useful is this rate expression? About as useful as this one was. You didn't know what those orders were. We don't know what that concentration is. This does not allow us anything useful. We're going to have to try and work a little bit harder to make a rate expression that is useful. Okay, so if your slow step happens later in the reaction or not at the first step, we now have to shift to something else. What's that something else? Extra piece of information. We assume every step before it is so fast that it reaches equilibrium. At equilibrium, what occurs? The equilibrium constant equals the products over the reactants. Does the equilibrium constant show up in our rate expression? No. So while that is a valid statement, that doesn't help us. What else do we know? Why is the equilibrium constant valid? How did we initially solve for the rate or the equilibrium constant? I know that pulls way back at straws, and we only spent maybe 15, 20 minutes looking at that. The equilibrium constant was solved for when we grouped the rate constants versus the concentrations. Meaning, at equilibrium, the rate of the forward, so the rate for step 1 equals the rate for the reverse. What is the rate for the forward reaction equal to? So that would be rate 1 equals K1 times the concentration of Cl2. To what order? Why is it first order? Why can we use the coefficient? It's an elementary step. That needs to equal now the rate for our reverse. What's the rate for our reverse? The rate constant for our reverse direct reaction times the concentration of Cl. What's the order? Why do we know it's 2? Because the coefficient is 2. Why can we use the coefficient? Because it's an elementary step. Okay? The reason we go through and do this is we now have a new equation that tells us the concentration of chlorine. So I can go through and now solve for the concentration of chlorine. Concentration of chlorine will equal K1 over K minus 1 times the concentration of Cl2 square root. Now that I know the concentration of chlorine, I can sub that back into my expression. And we know K2 times the square root of K1 over K minus 1 times the concentration of Cl2. Do that right? Yeah. Times the concentration of CHCl3. Do I know the concentration of CHCl3? Is that something in my overall equation? Yes. Do I know the concentration of Cl2? Yes. If I know those concentrations, I can look at the rate and I can then solve for this big knot of constants. I may not be able to solve for them individually, but I don't need to solve for them individually to make this useful. I just have to solve for the group. A constant times a constant is a constant. Divided by a constant, still a constant. Okay? We now have an overall rate expression that we could go through and solve or answer questions about. Okay? I'm not going to go through and do this one because I would never ask it, but what happens if we said that last step was the slow step? Okay, do we know the concentration of Cl? So if we said our last step was the slow step, that means we would have to look at the rate expression for our slow step. Rate equals K3 times concentration of Cl times concentration of CCl3. Do we know the concentration of Cl? Does that show up in our overall rate expression? No. Do we know the concentration of CCl3? No. What does that mean? We now have to assume every step before reaches equilibrium. So you would go back to K2, go through and say those reach equilibrium, set the rate of the forward of K2 equal to the rate of the reverse, and try and solve for either Cl or CCl3. You'll notice both of them show up in K2. So what does that mean you have to do? You go back to K1 and you solve for the concentration of Cl all the way back in K1. You then substitute all the way back down through your equation until you get to your overall rate expression. That is a beast of a problem. Right? If you can do that, you know how to do all of these problems, you should be fine on the test. If you don't know how to do that, you might still be fine on the test. Okay? Because that's still just a lot of work. Okay? Questions about that? No questions? Okay.
So why do you assume it was the second?
You had to wait till I deleted it. What was the question?
Just how do you know it was the slow step was the second one instead of the third?
You were told that.
Oh.
Right. So in that problem, you were definitely told. If you were given experimental evidence, you would have to look at what your rate would solve for and then say, does that match the experimental evidence? Okay, so you would come up with a rate expression for multiple different options, slow versus for the first step, slow for the second step, and then see how that matches with the experimental evidence. Okay, which is something that you did do in the homework. You tried to match mechanisms to individual reactions. Other questions about that? Okay, the other big thing that we pulled from our kinetics chapter was our integrated rate laws. So we've got our first order and second order. Don't know why I didn't show the zero order one up there. But what we've gone through and done is integrated our rate expression with respect to time. And we solved for the overall equation. And these are the equations that we came up with. Right? These become helpful because we can then solve for how long a reaction will end up taking if we know some concentrations and some rate constants. So that can get us out of lab faster. We went through and took this even further in the chapter 19 with our first order rate expression because that now allowed us to determine how much radioactivity is still present. Okay? Either how much or how old the sample is or how long something's going to be radioactive. We can come up with all sorts of different ways to solve that. From these, the biggest expression, let's see, put a slide on this. Okay, the biggest thing that you need to remember is what's going on at your half-lives. This is something I fully expect you to know. You're not given that equation. Okay, you have to know what a half-life means. So it's just an English thing. At the half-life, Okay, now we're saying we're at the time where what is true? We have half of our remaining species. Which means if we go through and solve for it, if T is at the half-life, then the concentration of our species at that point must be half of what it started with. We can use this to substitute back into either equation to go through and solve for different variables or terms. What if we were at the third life? What does the third life mean? We're at the time where we have a third of the species remaining. Okay? So that interpretation is critical to being able to manipulate these. You can fully expect to see that show up on your test. Questions about that as I continue on to the next slide? Yeah.
With the decimals, 67%, something left, or anything like that?
So if we're looking at percentages, if we say 67% of the sample is left, at what time is 67% left? What does that mean?
Do you go from the 67% left, or do you do the other?
So it depends on the way the question is phrased. And those can be very confusing. So it will be phrased very clearly. If I say 67% is left, what does that mean? What would our equation be? We want the time at 67% left. Whoops. What is A sub t? %, of what we started with. Okay. And yes, I fully admit those percent questions can get tricky to deal with. Okay, so when you go through and solve those, it's not a bad idea to solve them both ways and see if both answers show up on the exam. Okay. Other questions about our rate laws? I think that was the end of that chapter, wasn't it? Oh, not quite the end of the chapter. Remember, kinetics just tells us about the activation barrier. So we can go back and solve for the Arrhenius expression and see how energy gets folded into this. Please say I've got that. Okay, we can go through and come up with that straight line. That's how we could solve for our activation energy. Oh, man. I didn't put it up there. Okay. The whole point of that activation energy section was really looking at the energy diagram. So if we start at our reactants and go to our products, what does kinetics tell us information about? Where does kinetics exist in its happy little home? It's looking at the energy to go from the reactants to the transition state. Okay? Kinetics tells us about the relationship between the transition state and either our reactants or, for that matter, the product. Okay? If we change our perspective. Okay? It tells us nothing about the relationship between the reactants and the products. It just tells us the relationship to the transition state. Okay? So that's what that EA is our activation barrier. That energy difference between our whatever we're looking at, reactants and transition state, or our products in transition state. Okay? This curve we went back to several times in the semester. Hopefully it does show up in the slides when we look at the thermodynamics chapter. We can go through and put some more information into it. Okay? Questions about what's going on with our activation energies? Okay. Mechanisms, we actually just talked about this. So our rate law is always going to be determined by the slow step. There's two ways that we can end up seeing this problem fall out. I guess, go through. If our slow step happens first, it's nice and straightforward, simple. We just say that our overall rate is equal to the rate for our first step, and we're done. Okay? If our slow step happens later in the reaction, it gets much more complicated, as we just saw. You'd have to go through and assume that earlier steps reached equilibrium. Once they're at equilibrium, we can then go through and solve for unknown variables and plug stuff in. Okay? So we have to assume that equilibrium to be able to solve these. Questions about that? I don't feel like solving another one of those. Okay? We then shifted into the equilibria, or chapter 14. I think it was 14. At that point, we know the rate of our forward equals the rate of the reverse. We went through and did a solve to try and determine what was going on with that. And what we ended up finding out is that it ended up coming out as products over reactants equaled some constant. Okay? In this case, we've now changed our perspective a little bit, so we have to be careful. If we're asked for an equilibrium expression, what are we going to solve for? The equilibrium constant. You're now going to be solving for capital K. It is much different than the rate expressions. Keep them separate. In this case, when we go through and look at the equilibrium constant, we have to evaluate how our products and reactants interact with each other. Okay? And that's why we see that new expression where we have products over reactants. Okay? As far as some rules that apply to that, the only things that show up are aqueous compounds and gases. We do not include solids or liquids because their concentrations through the course of a reaction effectively stay constant. So we don't have to worry about them. We can group them in with our equilibrium constant. We don't have to stress about dealing with those numbers. If we look at the forward versus the reverse reaction, what's the relationship between them? All we've done is flipped them. Okay? It's the inverse. If we looked at the reverse reaction, we'd have reactants over products, as opposed to products over reactants. The way to do that mathematically is just to multiply or hold it to the inverse power. So we get that -1 show up. What happens if we multiply that reaction by a whole number integer? So let's pick that top reaction and say, I want to multiply everything by 2. What happens to the equilibrium constant? What's the coefficient now? What's the exponent on D? 2 times D. What's the exponent on C? 2 times C. So when we go through and multiply by a whole number coefficient or a whole number integer, it's the same as holding our old equilibrium constant to that power. Okay? You saw the manipulation of those two things in that test, which I somehow completely goofed the answers on. You need to be able to manipulate those. Okay? If you have questions about that, not a bad idea to go back through and try and solve that problem for an answer that's correct. If you need to look up that or you need to check your work, you can check with me. Okay? What happens when we add two expressions? Because I don't think this is on the slides. What do we do to our equilibrium constants if we add two reactions? You multiply them. Okay? That can all be discovered by taking some random equations and adding them up to get a total reaction. Okay? And you will see that what you have to do is multiply to get that expression. Okay? The other big thing we picked up in chapter 14 was the introduction of ice tables. So we need to watch out for stoichiometry when we go through and deal with the change. At least in chapter 14, we really had to watch out for that. Okay? Chapter 14 in the tail end of 17, 16, 17, one of those numbers. Okay? Why? If we look at the reactions in chapter 14, our coefficients weren't always 1, which means if one increases, say if we look at an individual reaction that says, whoops, we went from 2A to 3B. If I react 2 molecules of A How many molecules of B do I get? 3. So if A goes down by 2, B must go up by 3. So you have to make sure those coefficients show up in your change. Where else are those coefficients going to bite you? We write out the K expression for this. It's K equals B, so products over reactants. What's the other thing we have to be concerned about? The coefficients become our exponents. Okay, so they will show up twice. You need to make sure that you take them into consideration. They are being applied in 2 separate conditions. It's very easy to leave them off in one case or the other. So make sure they show up.
That's
Yes.
if that reaction was at equilibrium, right?
Yes.
There'd be an air going up.
We would, oh, I see what you're saying, yes. We would have to assume equilibrium for this. Why? What is E in our ice chart? Equilibrium. The whole reason we go through and solve an ice chart is to get the equilibrium constant or concentrations so that we can use the expression K equals B cubed over A squared. Okay, because what is K? The equilibrium constant. That's only valid when we get to equilibrium. Yes?
Would it be 3B cubed over 2A squared?
It depends on what's going on with how we had to solve that problem. Okay? And that's why it gets a little bit dicey, because in some cases, you don't need to worry about the change. Maybe you're given the equilibrium concentrations. If I tell you the equilibrium concentration of A is 3 and B is 2, when I go to plug in numbers, do I do 2 times 2? What would I plug into my K expression? K equals, what's the concentration of B at equilibrium? 2, whoops, cubed. Oh, that's a bad cubed. Over 3 squared. We don't have to worry about the change. Why not? Because I gave you the equilibrium concentrations. There's no need to do anything with the change. When the change is used, you must go through and plug it in appropriately. So if we went through and solved this and we said, just to give something to work with, if we look at our change, what's going to happen? We're going to shift towards products or reactants. Products because Q is equal to 0. If Q is equal to 0, it is by definition less than K, which means products must form. So B goes up, A goes down. How much does A go down by? Okay, we have to be careful with how we go through and solve this. If we say 2x, what does B go up by? Make sure I did this right. Oh, it does work out that way, right? If we convert, for every 2 moles of A, there are 3 moles of B. So what's the change? 3x. Okay. Remember, our changes are 151 calculations. We're just trying to do a unit conversion from moles of one species to a moles of another. What if we'd went and put in x? Now what happens? What does B go up by? 3/2 x. Go back to our conversion that we've got in the upper right-hand corner. If I said x, if A decreased by just x, then I get 3/2 times x. To make sure that what you establish x to be accounts for all of your conversions. Okay? This comes important when we look at equilibrium. Well, when we look at equilibrium problems, also with acid-base problems, if you go through and put in an x and you end up needing to solve for that x value, you need to know what you set x to be. If I asked for the concentration of B, okay, if I go through and solve this problem right now, I get x. Is x equal to B? No. 3/2 times x is equal to b. That makes sense? So whatever you decide to be your change, you need to make sure that you apply that appropriately when you try and solve for your answer. So there's various methods that you can go through with that x. You can choose different variables or different changes within those. Just make sure that whatever you choose, you answer the question according to what the question asked for. Okay? And that's what that last statement is. Watch out for the stoichiometry in the change, and then make sure when you solve a problem, you know what you set x to be. X will be different, not necessarily for everybody, but you can make x different for every single person. Okay, so make sure you solve for the correct thing. Questions about that? We could go through and look at kind of an easier problem. If we looked at a mixture of these kind of compounds, we're told an equilibrium concentration. Everybody likes to go through and start immediately solving for an equilibrium constant. Okay? Do we want the equilibrium constant? I lied. Yeah, in this case we do. To solve for that equilibrium constant, what do we need to know? We'd have to know the equilibrium concentrations of everything. Okay, so we could go through, set up an ice chart, take all the information that we know, set everything up. Let's see, come on. There we go. Plug in all our numbers. We would need to know that bottom row. That is a row, yes. At this point, all we know is the concentration for NO. How do we figure out the concentrations for everything else? We could go through and put in our changes. Well, step back. Can we figure out the change for any one of those? We could figure it out for NO. Why do we know NO's change?
0.1.
Because initial plus change equals
0.06.
equilibrium. That's why we build the chart, so that we can format how our calculations come together so that we can see what's happening with our individual work. Right? You don't need the chart, it just happens to format it easier, which means we can solve for our change. If we know the change, we then need to convert the change for each of the other things. So when we go through and convert 0.038 moles of NO into moles of H2, what do we have to do? We use our coefficients from our balanced equation and set up our conversion factor, and we can solve. We can do that with all of them. Okay? Same idea there. Again, the conversion factor. There's no x in this case, but we still have to know those relationships. Okay? Once we know all of our change numerical values, we now know the equilibrium concentrations, and we can solve back into our equilibrium constant expression. When we plug it back into the equilibrium constant expression, what things do we need to watch out for? The coefficients again. That's an eraser. The coefficients again translating to exponents in that K expression. Yes, no? We could have used x. Right? We go all the way back to the beginning. Come on, go back. Stop. We could go through and put x right here. This is negative x. This is plus some x. What does that coefficient need to be in front of the x? Same thing, right? It's a 2 to 2, so it's 1. What is, oops, sorry, thank you. Since we moved to our products go up. Goes up by what? Goes up by some amount of x. What is that amount of x? 1/2 of x. Next one goes up by x. We could go through and solve for our equilibrium concentration. 0.05 minus x, 1/2 x, 0.1 plus x. If we plug those into our equilibrium expression, it asks for the equilibrium constant. Do you know what x is at this point? No. So we had to do something else. How did we get the 0.05 minus x, the half x, the 0.1 plus x? What did we do? How do we get those numbers? I got all day. We did initial plus our change. So what would this value be if we ignore that number for the moment? What we would have written is 0.1 minus x. What does that equal? 0.062. How do I know it equals 0.062? That's what the problem told you. Can you solve for x? Yes. Once you know that x number, you can go back in and substitute in each of those cases. So we could still use x. It just depends on what point do you see the answer pop up. Okay? So when I solved it initially, I saw right away that I could solve for x immediately. I didn't need to go through and plug in x's for everything else. If you don't see it, plug in x for everything else. Get to your equilibrium concentrations and then say, well, crap, this problem sucks because I don't know x. Is there a way to find x somewhere else? That's when you would then go back and say, yes, initial plus change is equilibrium. Now I can solve. Does that make sense? Other questions with your equilibrium? Then we got to go all the way back through this. Whoop, oh, come back here. Okay, so at that point we could go through and solve for that. Depending on the sig figs, you may see various answers there. In most of the exam, I try to give you at least 2 sig figs because 700 or 7 times 10 to the second doesn't look an awful lot like 653. So if the sig figs aren't quite matched up right, that might be why. Okay, so I try and set it up so that when you enter in your calculator, your number comes out reasonably close within simple rounding or obvious rounding of the answers on the exam. Okay? How many of you would bubbled in 7 times 10 to the second as an answer? Okay? The sig figs there seem pretty far off. It does round appropriately. It's just not super obvious. Okay? Questions about chapter 14? Okay. Well, we then, yes.
No, I have a question in regards to something similar to that, say on the exam.
Yep.
On chapters 18 and 19, like the Connect, instead of writing in E for electron, it made us put in the beta sign. Are you going to be that particular on the exam?
No, and on the exam, there's no way I'd be that particular. If I was that particular, you'd see it. There's no way on any multiple choice exam I would give you what is the particle emitted from this and then give you beta and E.
Or like say,
That's
if we have
just
to write
rude.
something in, if we read an E or a B, same thing.
It's going to be the same thing. I'll give you the same credit. Okay. We won't look at 15 and 16 because we did that yesterday. So unfortunately, I won't talk any more about that. You don't have any recordings of that. For chapter 17, remember all of your definitions. We went through and covered a lot of things with that. Enthalpy was a review. The new stuff was your entropy and your Gibbs free energy. Standard state, I'm pretty sure, was a review as well. But I don't remember what standard state was defined as in 151. I think it's probably the same. All right. So make sure you know what each of those terms mean, what the different signs mean, how different things line up versus not line up. Okay? When we look at entropy, because entropy was a new topic, we spent a reasonable amount of time looking at that. We're looking at a measure of disorder. Okay, that's the way most people seem to remember it. I don't like disorder because it brings in that negative. Dis is a negative, which means if I'm trying to get a measure of disorder, I'm looking at the measure of some negative value. That's a bit confusing for me to wrap my head around. So I look at entropy as a term of motion. If we increase motion, we're increasing entropy. If we decrease motion, we are decreasing entropy. Okay, so to me, that just makes a little bit more sense. We looked at some qualitative analyses. So you've got 4 rules that you had to go through and apply for each individual reaction. The two easiest ones are your phase and numbers, but remember, complexity does play a role. It played a role actually on exam 3. One of your questions had you determine a decrease in entropy based on the complexity of your reactants versus products. Okay, so a bit sneaky, but it can show up. The first two are easier. Mixtures, that's a long shot. Okay? As far as units go, you typically see entropy in units of joules, which makes things difficult because when you look at enthalpy, typically we see large changes in entropy or energy when we're looking at an enthalpy, or for that matter, Gibbs free energy, which means the units in those cases typically are in kilojoules. So watch out for conversion issues when dealing with thermodynamics. There's not a whole lot of mathematics, so ultimately you're just plugging and chugging. You have to make sure that your units match up. Hey, we get right back to that unit conversion issue. Okay, so watch out for those units when you go through and solve. Yeah.
I get confused when it says the decrease in entropy of the surroundings compared to, is it the reaction? What's the opposite of that?
So when we go through and look at any given reaction, if the heat goes up, what had to happen? That heat had to come from somewhere. We can't just create heat. So if the energy goes up in the surroundings, if we see the temperature go up, what did the reaction have to do? The reaction had to do the opposite. It had to lose that energy to the surroundings. Okay? Because we can't create or destroy matter, changes of the system versus changes of the surroundings need to come out to be zero in a theoretical world. Right? So when we go through and apply, the change for an overall reaction is going to be the system, or your reaction, plus the surroundings. You add those two terms together and you get the net result in the universe of that system. Okay? So yeah, that is difficult to apply. So if we look at entropy, if the entropy decreases in the reaction, what happened to the surroundings? The surroundings must increase to account for that decrease. If your reaction increases, what happens to the surroundings? Surroundings must decrease. And it comes back to that conservation of energy, ultimately first law kind of stuff. Okay? And our second law of thermodynamics actually tells us that it's increasing is favored. So if we look at a large enough universe, we look at the whole universe, entropy will always increase. It can never decrease. And that's a pretty large scale system. Okay? Important equations. I'm pretty sure all of these showed up on your exam. Instead of A on your exam, we saw X. The reason I showed X is then I didn't have to write this equation 3 or 4 times over. What could X equal? S, H, and G. Okay. What does that weird look, capital E look or mean? Sum. So all we're going to do is add the whatever unit or whatever system of our products, and we'll subtract the sum of our reactants. The one thing that you've got to watch out for that a lot of people forgot on that last exam was this N and this M. What do those mean? Coefficients. Coefficients bite you in equilibrium, they bite you in thermodynamics. So watch out for them. You've got your Gibbs free energy equation, which shows up pretty much everywhere. You'll see that in multiple classes, so just be aware of that. That's probably one thing you should absolutely have memorized. You've got some other equations. Again, it's largely just plug and chug when you look at these. The issue that you've got to watch out for, your conversions. Make sure you're using the appropriate units for each reaction. It's the only way these problems solve. So if your units don't match, you will get the wrong answer. So go through and make sure it cancels out to give you the correct units. If it doesn't cancel out, then you did something wrong. Your units can solve or show you that you were wrong. We did talk about the important relationships. These are critical to have memorized in getting through this class, or know how to manipulate that delta G equals know how to manipulate this guy. So you either have a good solid understanding of what are favored entropy and enthalpy changes, so that you can go through and determine signs and figure out what your delta G should be, or you've got them memorized. If you have to take any kind of standardized test, MCATs, PCATs, potentially even GREs, you will need these memorized. It will show up again. Okay? They're favorites of standardized testing because it involves no calculator. All you have to do is apply those signs. Okay? Told you we were going to get back to it. Remember, this curve is critical to this overall class. I mean, this is kind of the whole idea behind this class, is this diagram. So it's looking at energy on your y-axis versus the reaction coordinate. So as the reaction progresses, we shift from reactants to products. So we're looking at our reaction coordinate. And we can describe how that process occurs. In the top half of that, we're looking at kinetics. It's how everything is related to the transition state. So that has to be in the upper portion of our curve. Why is the transition state never in the lower portion of our curve? What would our activation energy be if it was in the lower portion? Has to be negative. We can't have a negative activation energy. It's an interesting question, actually. I'll have to look into that. You won't have a negative activation energy. Okay? So you need to be familiar with identifying the individual activation energies. The one labeled here is the activation energy for which reaction? Forward or reverse? Forward. How do we know it's for the forward reaction? Because it's the difference or the relationship between our transition state and our reactant energy. If we wanted the reverse, what would we need to look at? We would look at the difference in energy between our product and our transition state. This is now the activation energy for our reverse. Okay. Thermodynamics exists in this nice little happy space down below our curve when we're not looking at our transition state anymore. In that case, what we're defining is the Gibbs free energy. That's the difference between our reactants and products. Okay. That is Gibbs free energy. In most reactions, how big is the enthalpy? Big or small? Relatively big. How big is the entropy? Relatively small. So in a lot of future classes, you will see delta G simplified to delta H, because in most reactions, they are very, very similar. Okay? Please be aware, it is not the delta H, that is the Gibbs free energy. What we're doing by saying the delta H is that's a simplification. We're assuming the entropy doesn't change enough. Okay? So really what they're telling you is that 152 is pointless by writing delta H. Okay? Bit of a silly statement to make. Sort of. Okay? What other things could we identify within this? That was kind of an open question. I don't know what else to identify. Okay. We did use this curve to help us determine our Gibbs free energy. We related the activation energy of the reverse to our forward. So we can solve for all sorts of different things using this curve and finding those relationships. Okay. A lot of that came through the Arrhenius expression. Chapter 18 was our electrochemistry. You need to know your definitions. What definitions are we talking about? Anode, cathode, what else? Reduction, oxidation. What else? One more small one. Reducing agent, oxidizing agent. You need to know what those terms mean. I think I've got them all up here. So we're looking at each of these processes. Remember, I've set up some mnemonic devices here so you can try and memorize those a little bit easier. Do I have the... So our agents are up here. Okay. To make sure we apply those definitions appropriately. The other... Oh. Thought I was moving into the voltaic cell. Remember that you need to be able to balance reactions. When you're balancing reactions, the important aspect is determining the oxidation state. There are some things you need to have memorized. You learn these in 151. You get really pushed on knowing them or knowing how to solve for them in 152. Right? So remember, we have a difference between charge and oxidation state. Charge applies to a molecule. Oxidation state applies to an atom. How many atoms does it apply to? 1. The reason why I address that, go back to your exams. I noticed a lot of people had this issue with, it was H2, C2, going to CO2. A lot of people said, okay, well, carbon is a +6, carbon is a +4, that's a reduction. Is that really true? What is that +6? That is the charge contribution from all carbon atoms. How many carbon atoms are in that structure? 2, which means what's the oxidation state of that carbon? +3. You went from a +3 to a +4. What was that? That's an oxidation. Okay? So remember, oxidation states apply to a single atom. If there's multiple atoms in your formula, make sure you account for those when you go through to determine your oxidation state. Should we go through and solve the oxidation states for, what is that, oxalic acid? I heard a no, pretty emphatic one, so go ahead and skip on. Balancing your half reactions, it helps to split them into the half reactions first when you go through to balance your redox reactions, so split them up. Balance the elements other than oxygen and hydrogen, then balance your oxygen by adding water, then balance your hydrogen by adding H+, then, like we've already addressed when we did the electrolysis question earlier today, then you can balance the charge by looking at your electrons. Okay? So again, notice where that electron balancing shows up. It shows up at the end of balancing your half reaction. At that point, since we're looking at a redox reaction, we need to go through and make sure that our electrons cancel out. In an individual reaction, we cannot have a single reduction. We cannot have a single oxidation. They must be partnered with something else, even in the electrolysis. Though in the electrolysis, we typically ignore the other reaction. Okay? So you need to go through and pair them up and make sure that the electrons cancel out. That's going to require multiplying by different integers. Add everything up, simplify where you can, and then check your work. Remember, atoms must balance across the reaction. Electrons must balance across the reaction, and your charge must balance. If any one of those is wrong, what does that mean about your answer? It's also wrong. Okay? I'm pretty sure I'm not going to be able to get up through all of this. Remember your parts of the voltaic cell. Okay, so this slide is actually probably one of the better ones as far as memorization for your voltaic, for your chapter 18, because it gets your cathode in there, telling you that you're looking at reduction, so a nice pretty red cat, or scary red cat. And anode is where oxidation is occurring. It's where you get anox. Okay, so you get Babe's blue ox to help you remember that. Loss of electrons, Leo or oil, gain of electrons, Gur or Rig. Okay, you need all of those individual pieces memorized. You need to know those to be able to apply these. With the salt bridge, it's an interesting question. If we look at our graph or our chart there, whatever that thing is, thing in the middle, the picture, we're looking at the motion of ions. We need ions to flow against the current of electrons so that we end up with a neutral charge. So look at an individual reaction, decide what's happening at each electrode. For our zinc anode, what reaction occurs? Oxidation, which means it is losing electrons, which means the charge at that cell becomes positive. How do we stabilize that positive? Okay, we can't add electrons. Those electrons are leaving, going the other direction. So we have to balance that electron flow with ions. What ion it has to move towards it? A negatively charged ion. In this case, nitrate shifts towards that electrode. Okay? If we look at determining mass changes, look at the reactions occurring at each electrode. At the anode, what happens to the zinc solid? It becomes zinc ion. So what happens to the weight of that anode? We start with a solid and it goes into solution. Well, the solid is now disappearing, which means mass is decreasing. So look at the reactions to try and help you determine that. We're definitely out of time. I think there's another like 10 slides maybe in the review. If you've got questions about anything, please send me an email. I do apologize for not responding to the discussion boards. Been too busy trying to get through lab reports. I will try and be responding to the discussion boards this afternoon to try and give you some feedback on what answers have been posted up there if anything's blatantly wrong. Okay? If you got questions, feel free to come up and ask.